You are starting a journey into a world of senses different from your own. How do birds perceive the world? Even a starling responds to many more sights and sounds than we do. We experience life through 5 main senses, but even these are better developed in some familiar animals. A mere goldfish can see colors invisible to us. A dog lives in a world dominated by smell. It's a million times more sensitive to some odors than we are. Compared with many animals, our sense of taste is surprisingly crude. We may be aware of the touch of a mosquito, but we're insensitive to its sound world. Perhaps compensating for our limitations, we sometimes search for a mysterious 6th sense. For many animals, an extra sense is a reality. We may look to the stars to divine our future, but they were used by birds as a more practical guide long before mankind existed. Migrating birds use these constellations to navigate. Although each day the sky patterns appear to rotate, the North Pole star remains as a constant reference. At dawn, another celestial compass is revealed. The position of the sun is another vital aid to navigation. Although the sun changes position throughout the day, the bird's body clock allows for this movement and helps to keep the bird on course. When these cues are obscured, the birds fall back on a 6th sense, one that detects the magnetic force lines of the Earth. By sensing the angles these lines make with its own body, the bird maintains its direction. As it faces south, so the lines arc away from it. These force lines surround the Earth as they would a giant magnet, and so always indicate the position of the Earth's magnetic poles. With the help of this magnetic guide, barnacle geese navigate the 1,800 kilometers from Greenland to Islay in Scotland. Even greater feats of navigation are shown by the creatures of the sea. In the murky depths of the oceans, there are few visible features to help the animals navigate. Here, dolphins and whales are thought to use magnetic landmarks instead. Variations in the strength of the Earth's magnetic field create an invisible landscape of hills and valleys. Just as we use the contour lines of a conventional map to indicate altitude, so these contours show magnetic strength. The dolphin is thought to follow these contours to find its way around. Just where a dolphin's magnetic sense organs are located is still a mystery. The magnetic sense of some fish is less mysterious. The ray can also sense the Earth's magnetic field as it swims through it. Tiny pores around the mouth are the organs sensitive to any magnetic or electric field. They can even detect the tiny electrical discharges produced by other life forms. By sensing such muscular discharges, the thornback ray finds its food. It lives on crabs and other crustaceans. In the streams of Australia, there lives perhaps one of the strangest of all living animals. The platypus, although a mammal, lays eggs like a bird and also has a bill like a duck. It can search for food with its eyes shut, because the bill is a remarkable organ. Not only responsive to touch, it can sense the electrical discharges of freshwater shrimps. Although the shrimp's movements generate fields of less than 1,000th of a volt, the platypus can detect these minute bursts of energy from over a meter away. For the shrimp, there is nowhere to hide. Among mammals, the platypus's electric sense is unique. Among fish, it's relatively common. Some African lakes contain over 200 species of electric fish. The elephant trunk fish uses this sense to find hidden insect larvae. All life generates electricity, either through nervous impulses or muscular discharges. Remarkably, many fish harness their own electricity for navigation. Modified muscles generate a 3-volt field which is warped by any object the fish passes. Rocks and plants all conduct electricity differently. As they distort the field, the fish creates an impression of its surroundings based on conductivity. The long body of the electric eel contains a battery of modified muscles. More than half its length is devoted to the generation of electricity. It too uses a low-voltage electric field to navigate. By stepping up the voltage, it can also use electricity to stun. The final bolt delivers 500 volts of energy. Electromagnetic waves from a storm radiate for hundreds of kilometers. They not only cause radio interference, they appear to affect animals too. Beekeepers notice that bees return to the hive and become irritable before a storm breaks. Bees either detect the electromagnetic waves directly or sense the changes in the static electricity of the air. The same electrical charges may affect our moods as well. Ants are also weather sensitive. This winged male is being returned to the nest by a worker. It had tried to leave before weather conditions were right for mating. These winged ants are the breeding forms of the colony, and they emerge for only one day. Sensitive to minute changes in humidity, temperature, or atmospheric pressure, they spend many weeks waiting for the perfect mating weather. Prompted by these unseen signals, they make their way to the surface. Ants from nests covering many square kilometers emerge simultaneously, maximizing their chances for mating. They need calm and stable conditions, for mating is carried out on the wing. The ants swarm over huge areas. There is safety in numbers, for predators account for comparatively few of them. A good weather sense is also vital for a bird's survival. Migration is potentially hazardous, so in autumn birds like house martins and swallows wait many days for perfect conditions. They need rising pressure, falling temperature, and winds blowing to the south. Only when these conditions are imminent will they begin their long migration. Their weather sense is believed to respond to changes in barometric pressure. This sensitivity may also give them information about the pressure changes of altitude. While on migration, birds continually adjust their flying height to make the most of favorable winds. They also change course to avoid bad weather. With stops en route for refueling, house martins take some weeks to complete their journey to Africa. The efficiency of flight relies on sensing air currents. Birds have many flight techniques. Large birds, like flamingos, save energy when they can by gliding. But they need to flap their wings to maintain height. Small birds, such as Quelea finches, use a form of bounding flight, folding their wings periodically to save energy. To maintain efficient flight, birds need information from air currents. Beneath its breast feathers, tiny feathers called phyloplumes monitor the changing eddies of air. This continual feedback gives the bird fine flight control. Like birds, the senses of insects are delicately tuned to changing currents of air. The locust's airspeed indicators are its antennae. As it accelerates, air resistance causes the antennae to bend. The locust compensates by slowing down its wing beats. It also uses vision to monitor ground speed. These flight checks help save energy. The locust's flight is so efficient it can make vast migrational journeys of several thousand kilometers. No animal is more sensitive to air currents than the scorpion. Fine hairs on its pincers can detect the air movements from passing insects. They monitor the air as the scorpion moves and help to keep it on course. For centuries, animals such as scorpions have been endowed with mystical powers. Some have even been credited with foretelling earthquakes or volcanic eruptions. The snake has this mythological reputation. With its body in continual contact with the ground, it can sense the slightest vibration, perhaps even the tiny tremors that sometimes precede a quake. Other animals also seem to anticipate earthquakes. Cattle stampede, cats retrieve kittens, birds sing at the wrong time of day. Heightened senses may account for much of this strange behavior. Traces of volcanic gases may warn of impending danger. Electrostatic charges in the air may provide another sign. Water animals can sense vibrations of a different nature. The gyrations of whirligig beetles create a flowing pattern of ripples. By detecting their watery echoes, the whirligigs can sense their surroundings. These pond skaters are using ripples for a more deadly purpose. The raft spider has similar skills. Hairs on its legs are sensitive to the slightest disturbance. A ripple sense has evolved to perfection beneath the water surface. The synchrony of the mackerel shoal is maintained by a ripple sense. Each fish creates its own bow wave. By reacting to the ripples created by others, a fish monitors its position in the shoal, even in darkness. The ripples are detected through the lateral line organ that runs the length of its body. As well as helping this synchronized swimming, the lateral line is used to sense the fish's surroundings. It's even sensitive to the movements of nearby predators. The grey seal is a master fisherman. Its success in even the murkiest of water means it does not simply rely on vision. Even blind seals are relatively common. The secret of their success lies in their whiskers. Not only sensitive to touch, they also respond to the slightest water movement, even the ripples of a fish. Although the fish's lateral line helps it to detect the seal, it cannot always escape. In the caves of Mexico, there are fish that construct a view of the world solely through ripples. The eyes of the Mexican cave fish have degenerated totally. Using only its lateral line, it can detect the smallest obstacle and negotiate its way around the cave. The powers of the vampire bat are legendary. But superstition ignores the facts of the vampire's real supersenses. Like other bats, it can navigate in total darkness using echoes as a guide. Once it has found its victim, the vampire uses a different technique to locate its food. The nose leaf is a sophisticated heat sensor. Insulated from the heat of the bat's own body, it is tuned to the blood heat of its host. It guides the vampire to those tissues richest in blood. The heat sense of some snakes surpasses even that of the vampire. The North American cottonmouth finds food by tasting the air or using sight. But just below the eye, a special pit provides a second image, an image formed from the heat emanating from its intended prey. Tracked by this pit organ, darkness provides no sanctuary for the rat. At the final strike, other heat sensors in the mouth ensure deadly accuracy. The shark, perhaps the most feared of all animals, has an array of super senses. It can smell blood from over a kilometer away. Its eyes are 10 times more sensitive to light than our own. It can detect subtle changes in the Earth's magnetic field. Like rays and certain other fish, it can also sense the electricity of life itself. Tuned also to the sound of swimming and the movement of water, the shark is the perfect killer. Electricity will guide the final attack. On its next journey, SuperSense will explore the world of vision. How do other animals see the world? Is their vision the same as ours? All animals see by gathering light rays, and although to a gorilla we appear very different, our eyes capture light in exactly the same way. But for both of us, the image received on the light-sensitive retina is not what the brain ultimately sees. It is upside down, and only the center shows any real detail. On the retina, this area contains a high concentration of light-sensitive cells. Full color and definition is confined to this inner circle. The brain not only inverts the image, but also fills in all the missing information. Also, like ours, a gorilla's brain is involved in judging distance. The right eye has a slightly different view from the left. From these two separate images, the brain constructs a three-dimensional picture. Judging distance becomes precise. The brain is involved in the vision of all animals, but away from our closer relatives, we can only guess at how less familiar eyes finally interpret the view they see. The starling's eyes are far more mobile than our own. They can be brought together to increase the overlap and so improve the central image, or be moved apart to widen the view. The eyes also converge when searching for food, and move apart to spot predators. Like most prey animals, the starling's eyes are placed to the side of its head to give a panoramic view. Eye movements add to the coverage. No animal has a wider view than the woodcock. Without moving its eyes, it can even see behind itself. The eyes, placed centrally on either side of its head, give total wraparound vision. With this 360-degree view of the world, the camouflaged woodcock shows no hint of movement as it watches for danger. The eyes of a predator face forward and concentrate on the scene ahead. A fox's view may be narrower, but it has little to fear from danger behind. Like many mammals, the fox has limited color vision, but like us, it sees true detail in only the center circle. The brain fills in the rest. The lion, too, has the forward-facing eyes of a predator. But its vision differs from a fox's in a way common to animals of the savannah. On this flattened landscape, prey animals always appear to be on the horizon. To take advantage of this, the lion's detailed view is elongated into a strip. This lateral strip gives greatly increased definition, and again the brain constructs the missing details in the surrounding areas. Like the eyes of all animals, those of the wildebeest respond best to movement. So the lion moves as stealthily as it can, making the most of any cover. The wildebeest's clearest view also lies in this lateral strip. The kill will also provide food for sharp-eyed scavengers. The vulture has perhaps the keenest eyesight of any animal. As the sun heats the ground, the birds rise up on currents of warm air. These thermals will provide uplift to heights of 2,000 meters or more. When they reach this height, the vultures will be able to survey many kilometers of savanna. With thousands of these flying eyes scouring the ground, no carcass will be left for long. Their renowned eyesight relies on a remarkable adaptation. The central portion of their view is magnified 2.5 times. On the retina, this enlarged area has a high concentration of light-sensitive cells. These resolve the finest detail. The vultures not only scan for carrion, but are also guided by the behavior of other animals. A gathering of other scavengers is a certain sign of food. They may search communally, but at the carcass, it's every vulture for itself. This eerie science fiction spectacle is caused by an intriguing science fact. Eyes adapted to darkness often have a mirrored layer at the back of the retina to reflect light. This gives the eyes a second chance to absorb even the faintest glimmer. Most nocturnal mammals show this mirrored vision. The net-casting spider needs neither mirrors nor artificial light to see at night. Its enormous lenses let through every available ray, and its retinas have huge light-gathering cells. In addition, its eyes have a totally overlapping view, doubling sensitivity. The spider can see in 1/10 of the light we need, so on the darkest night, it can still hunt. It first constructs a unique kind of web, one that is held by its legs. Poised like a miniature gladiator, The spider relies on good vision to entrap its victim. Its eyes are not only sensitive to light, but react to the slightest movement. Although far simpler, the spider's eyes are similar in design to our own, but there are many animals with vision that is remarkably different. The rising sun's light filtered by the atmosphere appears to us as red. Insects like bees are blind to this color, but they see parts of the spectrum invisible to us. Our color vision is sensitive to green, blue, and red, but the bee is sensitive to green, blue, and ultraviolet. With only 3 basic colors, we both create a full color picture, but the bee's world looks very different. The spectrum is shifted towards the ultraviolet, and its compound eye provides a far coarser view. Seen through a bee's eye, flowers become strangely unfamiliar. This ultraviolet bloom is actually a buttercup. These are perhaps the true colors of flowers. The colors we see have no real relevance. For these hidden hues have evolved to attract insects. It's not only bees that have this ultraviolet vision. To our eyes, male and female clouded yellows look the same. But to a bee or another butterfly, the ultraviolet courtship flashing of the male is strikingly visible. Insects are also sensitive to another kind of light invisible to us. Patterns created as the atmosphere polarizes the sun's rays. These patterns create a sky map which the bee can use to navigate. Although normally invisible to us, these patterns can just be made out with polarized sunglasses. The bee needs to see only a small portion of the sky map to find its way home. Like the bee, the water boatman has a compound eye. This consists of an array of tiny lenses. Although each lens views only a fragment of the scene, they combine to create a single view. The water boatman's eyes are tuned to the polarized light reflected from water. Our polarized glasses cut down these reflections, but the water boatman's eyes enhance them. They help it find new breeding pools. The dragonfly has the ultimate compound eye. Its vision is 4 times better than the water boatman's. Good vision is essential for this aerobatic marvel, for the dragonfly not only hunts, but also fights on the wing. 30,000 lenses gather enough information for skilled maneuvers. But this view is still 30 times poorer than our own. To match our eyesight, its compound eyes would have to measure 1 meter across. Like us, the dragonfly has eyes with areas of high resolution. These are used to spot flying insects against the sky, either food, mates, or rivals. Territorial disputes are resolved by air-to-air combat. The victor returns to patrol its territory. Birds have the most complex color vision of any animal. The light-sensitive cells of the eye contain up to 5 different color pigments. These pigments detect many more color hues than we can see. The cells of the eye also contain colored oil droplets. These act like miniature filters and reveal even more colors. While many birds appear to use oil droplets to improve their color vision, seabirds may use them for a different purpose. The eyes of terns have a high concentration of red oil droplets. It is believed that these act as haze filters, cutting out the reflected blue light of sea mists. For terns and gulls that feed communally, these haze filters may help individuals locate feeding flocks. The terns concentrate over schools of sand eels. As they hover, they use sight to single out a fish from the shoal. Their eyes cannot focus underwater, so they simply take aim, then dive. Although terns cannot cope with the change of focus needed below water, there are some fishing birds that can. Like most animals, a cormorant focuses light using both a lens inside the eye and a cornea on the outside. In air, the cornea starts to focus light, which is then fine-focused by a lens that can change shape. Underwater, the cornea can no longer focus, which is why we see only a blur. But the cormorant's vision is still crystal sharp. By distorting its lens, it can compensate for the now useless cornea and focus better than any other animal. A cormorant's eyes may outwit a fish, but in Mexico there are fish with vision to outwit birds. These strange floating blobs are actually eyes. This is what they see. The eyes belong to anableps, better known as the four-eyed fish. each eye is divided. The top half looks for predators such as birds, the bottom half looks for food. In this way, it can see food and danger simultaneously. This distracting display confuses the vision of predators both above and below the water. The Great Barrier Reef is home to perhaps the strangest eyes in the animal world. Their vision is as bizarre as their appearance. They belong to a creature known as a mantis shrimp. The central band of the eye is the most complex color analyzer of the animal world. As it sweeps the scene, it not only scans for visible colors, but also for ultraviolet and polarized light. The eyes are searching for anything that might be alive. Once it's found a possible source of food, an analyzer is swept across it. It then brings the second analyzer into play, lining up the scanning lines like the crosswires of a gun sight. In the dark and murky waters of the Amazon live fish with eyesight as formidable as their predatory reputations. In water colored red by organic decay, the piranha has eyes that can pierce the gloom. Its eyes can see rays of light invisible to us. Here, the light we see is rapidly absorbed, but far red light still penetrates. As they hunt for prey, these killing shoals rely on far red light to cut through the murk. For the catfish, there is no escape. Even a mere goldfish has the visual powers of a piranha. In our high-tech world, we use far-red light for our own protection. Many security systems use this light, sometimes known as infrared, to illuminate guarded premises. Invisible to human eyes, but picked up by special cameras, the far red light shows up any intruders. As the truck disappears into darkness, it is still seen by the security cameras. The goldfish's eyes can see it too, lit by the far red lamps. A visual system that evolved to cope with murky water is here paralleled by one of our latest inventions. But the goldfish has other visual powers. It not only sees far red, it can also see ultraviolet, a color at the other end of the spectrum. A creature we take for granted can see a greater range of colors than any other animal. On our next journey, SuperSense will explore the world of sound.